Welcome to the tutorial session 1. So, here we will look at the basics of acidity, basicity and related concepts. So, although organic chemistry is a prerequisite for this course, I thought it is a good idea for people to go over some of the basic concepts, so that we can all pretty much be on the same page when the advanced concepts are taught. So, acidity and basicity, these are very fundamental properties of a molecule, and they help us understand a number of aspects about the structure, and it also gives us an idea about how changing the functional group on the molecule can have a major impact on a property. So, before we go into these concepts, let us first define pH. So, pH is defined as negative log of concentration of H3O plus, and this is a definition that we have encountered 8th or 9th standard perhaps. And just to go over this, so pH 7 is considered neutral. So, you have it is neither acidic nor basic, and pH 14 is strongly basic, while pH 0 is strongly acidic. Okay. So, as we proceed from 7 and go towards the left, that is go to smaller values, the pH of the solution becomes more and more acidic. And similarly, when we start from 7 and go up to 14, the solution becomes more and more basic. So, keep in mind that this is a scale. So, the two lower bound and upper bound of the scale is 0 and 14. So, if you, and this is obviously operational in water, because you are looking at hydronium ion, right. So, therefore, pH, because since life as we know it exists in water, so pH becomes an important parameter for us to understand what happens inside a cell. So, in certain compartments inside the cell, the pH can vary, it can become quite acidic, and in certain compartments it can become a little bit basic. So, pH plays a very important role in many aspects of functioning of a cell. So, with that background, now let us look at what pKa is. Okay. So, if I take an acid HA or AH and if I dissolve it in water, we can write an equilibrium constant say such as this, where conjugate base is A minus and the conjugate acid is H3O plus. And now, if I have to write an equilibrium constant, the equilibrium constant would be A minus multiplied by concentration of H3O plus divided by concentration of HA times H2O. Again, this is pretty much stuff that we have learnt in previously in high school. So, since the water is a solvent and the concentration of water in aqueous media is 55 molar, and we can assume that it is a constant. And so, we can remove one of these terms, which is this concentration of H2O, because whatever we do, we multiply it by a very large number. So, we define this term called as Ka, which is nothing but the acidity equilibrium constant, which is nothing but concentration of the A minus, which is the concentration of the conjugate base, multiplied by the concentration of the conjugate acid divided by the concentration of acid. So, what we deal with here is typically very dilute solutions of acid, and what we determine here is, if we take a very dilute solution of acid, then one can measure what is known as the equilibrium constant and define it as Ka. pKa is defined as negative log of the equilibrium constant Ka. Okay. So, both these numbers Ka and pKa provide us a quantitative measure of how strong an acid is. So, if I have to look at how strong an acid is, then one would argue that if the concentration of A minus multiplied by concentration of H3O plus is a large number, right, which necessarily means that concentration of HA is small, then together the Ka value would go up. Okay. So, therefore, when the Ka value is pretty high, the acid strength is quite high. Okay. So, higher the equilibrium constant, the greater the acid strength. So, similarly, we look at pKa, and because Ka values are sometimes quite small, for example, acetic acid, the value is around 10 power minus 5, and it is difficult for us to think of differences between 10 power minus 5 and 10 power minus 4.8 and 10 power minus 4.7 and so on. What we refer to is usually pKa. So, pKa, because it is a negative log value, it makes it into a smaller number that we can easily understand. So, the pKa scale, so a unit difference in pKa means tenfold difference in the equilibrium constant. So, again we shall summarize some of the pKa values that we have encountered. So, let us start with something like HI, which is a very strong acid. The pKa value is minus 10, okay. And let us go to a very weak acid such as ethane, where the pKa value is 55. Okay. So, this number is quite absurd, that is, the concentration of CH3 minus in aqueous media is 10 power minus 55, which is essentially not measurable, but it is an estimated pKa value. So, if we look at some other reasonable molecules such as acetic acid, which we looked at earlier, the pKa value is 4.75. Okay. So, we shall come back to this pKa table once again later, but this is a experimentally measurable quantity, and therefore, pKa values serve as a very important guide to understand the properties of a molecule and how it changing a particular functional group can have a profound impact on a property such as acidity or basicity, or sometimes it may have no impact. So, both of these are important for us to understand, because when we want to understand, let us say, how a drug functions or how a drug distributes itself, one of the properties that becomes important is the level of ionization, which will depend on pKa. Okay. So, to understand how differences in acidity are going to manifest, we would have to figure out what is the important factor in determining the acidity strength. So, the most important factor in determining the strength of an acid is the stability of the conjugate base. Okay. So, that is basically Ha plus H2O is in equilibrium with A minus plus H3O plus. So, A minus here is the conjugate base, and the stability of this conjugate base, one of the most important factors in determining how strong the acid is. So, the more stable it is, the more this equilibrium is pushed towards the right and the stronger the acid. Another important factor to determine the stability of the conjugate base, an important factor in determining the stability of the conjugate base is the element on which the negative charge is on. Okay. So, more electronegative the atom or the element, the more stable the conjugate base. Now, we shall look at some examples and see how we can explain the trends in pKa. So, let us look at these numbers CH4, NH3, H2O and HF. CH4, the pKa is 48, NH3, pKa is 33, H2O, the pKa is 16 and HF, the pKa is 3. So, as we know from our fundamental concepts in general chemistry, the electronegativity of the molecule increases in the following order, that is, fluorine is greater than oxygen, greater than nitrogen, greater than carbon. Electronegativity, fluorine is greater than oxygen, greater than nitrogen, greater than carbon. So, therefore, you can understand that the negative charge that is formed on the element, that is C minus, N minus, O minus and F minus. F minus is stabilized far more compared to O minus, which is in turn far more stable than N minus and C minus. So, therefore, this trend in pKa can be explained by invoking electronegativity. The pKa values of HF, HCl, HBr and HI decrease in the order 3, minus 7, minus 9 and minus 10. Okay. So, here in order to explain this, we would need to invoke bond strength and delocalization of charge. So, the bond strength of HF is greater than bond strength of HCl, which is greater than bond strength of HBr, which is in turn greater than the bond strength of HI. Okay. So, therefore, this bond is much easier to break when compared to HBr and so on. And so, the pKa value is 3, minus 7, minus 9 and minus 10. The second concept that we want to bring in here is the delocalization of charge. If you want to understand delocalization of charge, then let us look at iodine, which is a much larger when compared to bromine, which in turn is larger than chlorine, which in turn is larger than fluorine. So, the negative charge is dispersed much larger in a much larger space, and therefore, there is more delocalization. In iodine when compared to iodide when compared to bromide, chloride or fluoride. So, this helps us understand the trends in the pKa values. The next example is a series of perchlorate and related compounds. So, here again the pKa values are arranged in HClO is 7.5, HClO2 is 2, HClO3 is 1 and HClO4 is a dramatic value of minus 10, right. So, there is a huge difference between HClO3 and HClO4. So, the way we would understand this is to draw the equilibrium HClO in equilibrium with ClO minus plus H3O plus. On top of this is water. Now, if you do the same analysis for HClO4 plus H2O going to ClO4 minus plus H3O plus, then you will understand that chlorate is actually a species like this, and this can participate in resonance, and you will have ClO minus double bond O and so on and so forth. Therefore, the negative charge on perchlorate is far more stabilized when compared with ClO3 minus, which in turn is more stable than ClO2 minus, which in turn is more stable than ClO minus. So, this helps us explain this trend in pKa. The next question is, the pKa value of ethanol is 15.9, while acetic acid is 4.8. How do we explain this? So, here oxygen is the atom or element that we are considering. So, therefore, there is no difference here pretty much. So, ethanol, the structure is OH plus H2O, which will give you ethoxide plus H3O plus. So, here the pKa is 15.9, whereas for acetic acid, which is whose structure is this, plus H2O in equilibrium with acetate plus H3O plus, the pKa is 4.8, right. So, one way we can explain this is that you can see that the element involved is oxygen in both cases, right. But one important difference between acetate and ethoxide is the fact that acetate can actually involve itself in resonance. As a resonance form you can draw this, and therefore, this is nothing but the resonance hybrid O minus. So, this negative charge is highly delocalized when compared with ethoxide, and therefore, one can understand why this acetate is so stable and the acid is such a good acid. So, this is actually quite similar to the example of perchlorate that we looked at in the previous case. The next case is RSO2OH has a pKa of 0, RCO2OH has a pKa of 5, aryl alcohols such as phenols have pKa of 10 and regular alcohols have pKa of 15. So, again this will have to do with the stability of the conjugate base. R C double bond O O minus, this we already looked at, exists as a resonance hybrid. S double bond O O minus is the structure of sulphite, and again this can involve itself in various resonance forms, and therefore, you can understand that this is more stable compared with the alcohol. Okay. And between a phenol and alcohol, since there is a scope of delocalization within the aromatic ring, the aryl alcohols, I mean the phenols are typically more acidic compared to aliphatic alcohols. The next example we look at is pKa amongst various carboxylic acids. So, here you see acetic acid is our starting point, the pKa is 4.76. Once I introduce a nitro group here, the pKa drops to 1.7, and also when I have a NMe3 plus, which is a positively charged amine, then the pKa is comparable in 1.8. I have an electron withdrawing group in cyano, the pKa is 2.4, and here is the electron withdrawing group of a carbonyl and the pKa is 3.6. So, in order to understand this, again we need to look at the resonance forms here. You have O and there is a negative charge that is formed, and the more stable this negative charge is, that is the more delocalized, then the more stable this species is. Right. So, therefore, if you see how a nitro group is going to pull electrons, it is going to pull the electrons from the carboxylate, and it is going to make the negative charge more delocalized. Similarly, a fully charged ammonium species is going to again result in significant amount of delocalization, whereas neutral electron withdrawing groups such as cyano and carbonyl are pretty good, but they are not as effective as a nitro group or a positively charged ammonium salt. So, this helps us understand the trend in pKa values. Now, let us look at another example of structural effects on acidity in carboxylic acids. So, here we have given 4 acids. So, the pKa of a starting molecule is 4.8, it is very similar to acetic acid. Now, when I introduce a chloro group at this position, then the pKa drops by a couple of units. Okay. So, 2 units of pKa means a 100-fold difference in the Ka, and pKa here is comparable to, there is a drop in the next case, but it is comparable to the acetic acid or the carboxylic acid, while last example the pKa is 4.5, which again is similar to what we would see with the parent molecule. So, the major difference in the pKa comes in the case of the second example, where there is a 2-chloro functional group. So, the way we understand this again is to look at how delocalization occurs. So, as we discussed earlier, this can be a resonance hybrid in the form of a molecule here, and this resonance hybrid, once you have an electron withdrawing chloro, it is going to pull electrons towards itself, being an electronegative atom, and therefore, this will be more stable when compared with the parent. Okay. So, that helps us understand why this molecule has a significantly lower pKa, or it is significantly more acidic than the parent molecule. Whereas, as the chloro moves further away from the carboxylic acid, the inductive effect goes down as the number of bonds increase, and so it helps us explain why there is a not a huge difference in the pKa values, because here you will have 1, 2, 3 bonds, and here you have 1, 2, 3, 4. Right. So, as the number of bonds increase, the inductive effect becomes weaker. Let us look at one more example. Here, this is an example of a carbon acid. So, if you take cyclopentadiene, the pKa is 15.5, whereas in the case of this cycloheptatriene, the value is 36, and trimethyl cyclopropene is 62. So, to put these numbers in perspective, CH3, the value is around somewhere between 40 to 50. Okay. So, compared to a regular alkane like methane, for example, there is a huge difference in the pKa when it comes to cyclopentadiene. So, cyclopentadiene is a significantly stronger acid when compared to a regular alkane. Okay. Whereas, in the case of cycloheptatriene, there is a drop and there is a shift of about 3 to 4 units perhaps, but in the case of trimethylcyclopropene, there is an increase in pKa value. That means, it becomes a poorer acid when compared to aliphatic or alkanes. Okay. So, this can be explained by invoking the concept of aromaticity. Again, because the anion that is formed is 6 pi electrons, and this, as we know, is aromatic, and aromatic compounds are generally more stable than the corresponding unconjugated or molecules. Therefore, the possibility of aromaticity enhances the stability of the conjugate base. Here, the compound is neither aromatic nor anti-aromatic, and the negative charge is not really planar, because it is assuming a puckered structure, and so there is no stabilization or destabilization, and so the value difference in pKa is not very large. In the last case, if you generate an anion, you generate a 4 pi electron system, which is anti-aromatic in nature, and therefore, it becomes very difficult to make this molecule, and the pKa value is substantially higher than the parent one. So, very similar to carbon or oxygen or sulfur based acids, we also have nitrogen acids. So, nitrogen acids, for example, ammonia, the pKa value has been around 33. Now, when you move to an amide, the pKa value is 17, and phthalimide, whose structure is shown here, the pKa value is 8.3. Okay. So, the trend in the acidity of nitrogen acids is quite similar to the trend in oxygen acids. So, the difference or the concept that we need to look at again is the stability of the conjugate base. So, with that in mind, let us look at basicity. So, nitrogen containing molecules such as amines are very unique. So, we just showed you that ammonia can act as an acid. Okay. So, this actually acts as an acid and produces NH2 minus. NH2 minus, the pKa is going to be, as we just looked at, is around 33, and so for this to occur, you need a very strong base for the deprotonation of ammonia to produce amide. However, what is more common is that you have ammonia getting protonated to form NH4 plus. So, here in low pH, that is below 7 for example, ammonia can be protonated to form NH4 plus. In mildly basic pH, it forms ammonia again. The pKa value of ammonium is around 9.2, and therefore, at higher pH, it is going to be neutral. So, with this in mind, let us define another equilibrium constant known as Kb. Much like Ka is for acidity, Kb is for basicity. So, Kb is nothing but you take B plus H2O, going to give you hydroxide and BH plus. So, here is the conjugate acid, and here is OH minus is the conjugate base, and the scale can be defined as pKb is nothing but minus log of Kb. Because pKa's are so commonly used, if we want to understand this in terms of pKa, since it is in equilibrium, we just have to swap the numbers. So, you can imagine this as BH plus H2O going to H3O plus B. So, here the acidity is defined in the following manner, which is H3O plus times B divided by BH plus. So, here pKa is nothing but negative of log of Ka. So, commonly pKa of a base is the acidity of its conjugate base. So, therefore, it is also referred to as pKAH. Okay. It is not a very commonly used term, but pKAH is nothing but the way how good acidity of the conjugate base. So, higher the pKAH, the better the base. So, what we need to understand in determining basicity is what happens to the electron density on the nitrogen when it is acting as a base. So, the lone pair on the nitrogen, if it is less available for protonation, then the molecule would be less basic, right. So, the nitrogen atom is attached to an electron withdrawing group. So, in such a situation, the lone pair on the nitrogen becomes less available, because you have an electron withdrawing group attached to it, and therefore, it makes it less basic. If the lone pair is on an sp or an sp2 hybridized orbital as opposed to an sp3 hybridized orbital, then it becomes less basic. If the lone pair is conjugated with an electron withdrawing group, not just attached and but it can also be conjugated to an electron withdrawing group, then again the basicity goes down. If the lone pair is involved in maintaining the aromaticity of the molecule, then absolutely you will find that the molecule is going to be very resistant to giving away this lone pair. So, with this in mind, let us look at some examples of pKa-H values. So, if you take this molecule here, which is trifluoro analog of ethylamine, you have CF3CH2NH2, the pKa-H of this molecule is 5.7, whereas if the CF3 is moved by one carbon to the left, then the value goes up to 8.7. So, here you can understand this because the lone pair on nitrogen is being pulled by induction by the fluorine groups, and since the number of bonds intervening here are increasing, the inductive effect becomes weaker, and so the pKa-H increases, and this becomes a better base. Very similarly, you have the example of the chloro, where you have 5.5 and 9.65. Okay. So, this helps us understand how changing the group on the to the neighboring carbons of the nitrogen can have an important effect on the basicity of the amine. Now, let us look at the example of cyclohexylamine and aniline. So, cyclohexylamine has a pKa-H of 10.7, whereas aniline has a pKa-H of 4.6. So, what happens here is that NH2 here is quite available for donation. So, in the case of aniline, since it is about 40 degrees away from being in the plane, it is not participating in resonance as much, but it does have the opportunity to have some delocalization. Therefore, the pKa-H of aniline is lower than the pKa-H of cyclohexylamine. The next question is explain the low basicity of amides. The pKa-H of amides is somewhere in the range 0 to 1. So, amides have the nitrogen is sp2 hybridized and it occupies a p orbital, but we also know that this amide can involve itself in resonance and it can form a structure such as this. So, therefore, the lone pair is not really available for the amine for the nitrogen on the nitrogen to donate. And so, indeed if the lone pair there is donation that occurs, you will form a positively charged nitrogen molecule such as this, which is going to be situated right next to an electron withdrawing carbonyl group. So, this is highly unstable and is quite unlikely that it will occur, and therefore, the pKa-H of this molecule is substantially lower, is somewhere between 0 and 1. Okay. For the next question, while amides are poor bases with pK 0 to 1, amidines, structure is shown here, are much better bases. So, we need to explain this. So, amidine, whose structure is shown here, is basically the nitrogen analog of an amide. In order to understand this huge difference of about 12 units in pKa-H, let us look at the structure of amidines. So, amidines have a nitrogen lone pair and they have a C double bond N. Now, this lone pair on this nitrogen can be donated to an acid to produce a positively charged nitrogen species as shown here, which can then subsequently delocalize by arrow pushing as shown here. It forms another resonance form, which is shown here. So, together you can propose that this nitrogen lone pair can move into this and form a double bond with this carbon, which in turn can pick up a proton from AH. So, this helps us understand why this molecule is substantially more acidic than the corresponding oxygen analog, which is an amide. Okay. So, similarly, if you push one more nitrogen into this C double bond N into this picture, you form guanidines. Guanidines have 3 nitrogens on them, and again by just showing a similar structure, you can infer that these are going to be substantially more stable. pKa-H of guanidines is in the range 13.6, which is again quite high compared to amidines. The next example, we look at imidazoline, whose pKa-H is 11, imidazole, whose pKa-H is 7.1, and how we want to understand this difference. So, in the case of imidazoline, it is a simple cyclic amidine and its pKa value is just what we would expect, is around 11, right. But in the case of imidazole, on the other hand, it is less basic, that is, it is more resistant to giving away its lone pair, because both the nitrogens that are attached to an electron withdrawing sp2 carbon. So, here you see this sp2 carbon and there is another sp2 carbon. So, since sp2 carbons are going to be electronegative and they pull electrons towards themselves, the lone pair on the nitrogen is less available for donation. Now, let us look at the next example of a cyclic nitrogen based base. So, pyrrole, it is an extremely weak base and the value is -4, whereas pyridine, the pKa is 5.2. Okay. But both of these are actually poor bases when compared to a regular amine whose pKa is substantially higher. So, the way we understand this is basically pyrrole has its lone pair involved in resonance and it can form a 6 pi aromatic system if I include the lone pair, and so therefore, this lone pair is not really something that is easy for donation. Pyridine, on the other hand, the lone pair is not involved in resonance, but since it is to a electronegative sp2 system, it is again less available for donation. Let us look at with this concepts in mind, let us look at another question. How do we improve the aqueous solubility of aspirin? Aspirin is very poorly soluble in water. So, if we have to address this problem, let us look at the various functional groups that are available here. Aspirin has a carboxylic acid, it has an ester, and we already know that carboxylic acids have pKa values somewhere between 3 to 5. Okay. So, if we were to make the medium slightly basic, or if the pKa, if the pH of the medium is a little bit higher than the pKa value, then it is quite possible or quite likely that the carboxylic acid will be deprotonated. So, what we need to do is to be able to increase the pH, that is, make it into a slightly basic pH, and then you can make it as a sodium salt of aspirin, which will be freely soluble in water. Next question is, how will you separate a mixture of the above components, that is naphthalene, pyridine and paratoluic acid. So, if you want to do this, let us again look at the functional groups here. This has an acid, this has a base, albeit not a very strong base, and it has a neutral molecule. So, if you have a mixture of these three components, the best way to do this would be to first dissolve this in an organic medium. So, in this organic medium, you will have all three components A plus B plus C. Let us call this as A, let us call this as B, and let us call this as C. Now, if you, let us say, to begin with, wash it with sodium bicarbonate, then you have the organic layer or the aqueous layer below, the organic layer above. Now, the organic layer will take an A, and since bicarbonate is a base, it is going to convert the carboxylic acid to carboxylate, and the carboxylate will remain here in the aqueous medium, and A plus B is going to remain in the organic medium. Now, what you do is you separate the organic layer, which will contain A plus B, and you get your C. To this organic layer, which contains A plus B, you treat it with a weak acid such as. So, now if you dissolve it in dilute HCl, then the aqueous layer which is here will contain B, whereas the organic layer will contain A. So, now you can separate these two by this process. So, by using simple acid base chemistry, we can separate complicated mixtures even if we are able to understand how the acid base properties are manifesting themselves. So, the next question is, codeine is sparingly soluble in water, how can we improve the solubility? So, codeine is this molecule that is shown here. It looks very complicated, but an important functional group here is the amine, the other one is a phenol. the others they are not really going to contribute to acid base. And so, as we have looked at earlier, what we can do is to treat it with a mild acid, and so this nitrogen is going to get protonated and it will form NMeH plus, which is going to improve the solubility. So, despite the structure being complex, you can make a very simple modification of adding an acid to make the molecule more soluble in aqueous media. So, now with this let us move on to the next question, which is if I take this molecule shown here and I add one equivalent of HCl, which of the 3 lone pairs are going to get protonated. So, if you look at carbonyl, carbonyl is a base, but it is extremely weak base. We already look at an amide whose pKa is somewhere between 0 and 1. So, it is also going to be a weak base. Now, the last option is an amine whose pKa is estimated to be around 8 to 10 or something like that. So, if I add exactly one equivalent of HCl, the first nitrogen that will get protonated would be the NH2 as shown here. The next example, we will look at 2 different alcohols. So, you have a phenol and you have an aliphatic alcohol. So, if I add one equivalent of hydroxide ion, if we were to look at what would happen first, then if you generate a phenolate, which is as shown here, and an O minus with an aromatic alcohol over here, we already know that a phenolate is actually more stable when compared with an aliphatic alkoxide. And so, I would expect that phenolate would be the only product that would be formed, that is you will get O minus CH2 OH, assuming that NaOH is the base used here. So, the next question is separate a mixture containing nonane and hexanoic acid. So, we already looked at the example of the ternary mixture. So, this is much simpler compared to that. So, here this is an organic soluble molecule. This is also soluble in organic solvent, but then we would treat it with a mild base and generate RCO minus, which will then be moved to the aqueous layer, and the organic layer will retain nonane.